Hello everybody. This is lesson 4 of the lecture Macroeconomics. I will address slide 1 to 25 in chapter 2, the long run development of economies. Before we start, let me give you an overview of this chapter. We begin with an exposition of the standard version of economic growth theory, the so-called Solow-Swan model. As we will see, this theory describes the empirical data quite good. It predicts that in the absence of technological progress, every economy reaches in the long run a so-called steady state, where GDP is constant. If there are, however, exhaustible resources which cannot be substituted by other resources or technological knowledge, the economy starts to shrink. This leads to the question how economic policy should respond to the problem of exhaustible resources. In section 2.2, I will therefore present a couple of different doctrines from this economic policy debate. Finally, in section 2.3, we will discuss the reasons for the long-term structural change in the composition of GDP, which we have already observed in chapter 1 when we discussed the long-run development of GDP by the production account. So let's start with the so-called Solow-Swan model. Why is the knowledge of the reasons for economic growth of importance? Why do we need a growth theory like the Solow-Swan model? Let's take a look at the long-run growth performance of the German economy as displayed by this diagram. A widely used convention in public media as well as in textbooks is the expression economic growth is used synonymously with real growth of GDP. Nobody measures economic growth based on the nominal growth rate of GDP. Therefore, this diagram presents German GDP at the prices of a fixed base year, namely the year 1995. The diagram reveals that the slope of the development of real GDP until the German unification, this line segment here, was significantly steeper as afterwards. Accordingly, if we calculate the yearly GDP growth rate, we receive 2.6% for the first 20 years on average and 1.1% thereafter. What does this imply now for the personal well-being of the people? The following calculation might give you an idea. Under a growth regime with 2.6% GDP growth, real income doubles every 28 years, which means your income doubles 3 times in an average lifetime. Under a growth regime with 1.1% GDP growth, real income doubles only every 63 years, which means your income doubles only 1.5 times in an average lifetime. From this point of view, I think it would be interesting to understand what has caused the worsening of the growth performance of the German economy after the unification. As we will see by the end of this section, the simple textbook version of the Solow-Svern model is able to provide an interesting answer to this question. So we will come back to this diagram later. Another way to look at economic growth is the comparison of the growth performance of different countries. This diagram compares the development of per capita GDP at constant prices from the year 1950 to the year 2010. The time series of every country is divided over its value in the year 1950. So every country starts with a level of 100% in the year 1950 here. All differences between the levels of per capita GDP observable in this diagram have built up since the year 1950. As is obvious for a couple of countries, these differences are quite large. While some countries like South Korea, Japan or Spain have increased their per capita GDP by factors 10 to 16, other countries like Bolivia, Venezuela or Uganda have experienced stagnating GDP levels or even a slightly negative GDP performance. If we had now a growth theory which is able to explain these differences, we could use it to develop policy strategies to help poor countries to improve their growth performance of per capita GDP. We will therefore analyze in the following the simplified textbook version of a growth model that goes back to the economists Robert Solow and Trevor Swan, the so-called Solow-Svern model of economic growth. As we will see in chapter 3, the underlying assumptions are identical with the so-called neoclassical growth model. The difference lies only in the point of view. While the neoclassical macro model describes changes and adjustment processes within a period, it is a static model. The Solow-Svern model describes the development of an economy over several periods. It is therefore the dynamic version of the neoclassical macro model. Basic idea of the Solow-Svern model is GDP will grow if a country is able to accumulate production factors from one year to the other. Accumulating production factors are not completely borne out in the production process of one period. For example, capital equipment like machines, production facilities, human capital, the knowledge and ability of humans, or technological knowledge, blueprints of new technologies, for example, or incorporated knowledge in machines. What these three production factors have in common is they are not completely consumed in the production process of, let's say, 1 year. A machine can typically be used over several years. The human capital, the knowledge of humans, is typically available over several years, and technological knowledge is perhaps an extreme form of accumulating production factor, since it is not consumed by the production process at all. To simplify the analysis in the following, we start with keeping all production factors but capital equipment constant. Later on, we will analyze what happens if one of the other production factors also changes. The other assumptions of the Solo-Swan model are identical with the assumptions of the so-called circular flow model, which we have discussed in Chapter 1. Firms produce GDP with the help of production factors. All production factors belong to households who are paid for their supply of these production factors by firms. These payments add up to total GDP. Households then decide how much of their income is consumed and how much of their income is saved. Savings are offered by household on the capital market as credits to firms. The capital market interest rate adjusts so that households' savings equal firms' demand for credits. Firms use credits to invest in capital equipment. The circular flow representation of the Solo-Swan model is therefore straightforward and quite simple. So we have the firm sector or company sector on one side of the economy, again like in the circular flow model, and the other side we have the household sector. Now we are in the first production period. Firms produce GDP, symbolized here by this cake. Households receive GDP as payment for the production factors they have offered, supplied to firms. Most important production factors is labor from households or savings from households. So this is supplied to firms. Firms use these production factors and pay households with GDP. Now households take this GDP and decide how much of this GDP is used for consumption purposes and how much is saved. Households offer their savings, here represented by this piece of cake, to the capital market. The interest rate takes care that savings equal investment demand, savings supply by households equals investment demand by companies. Now, if investment in machines, other type of capital equipment, production facilities, building, and so on, is larger than the depreciation of capital, the erosion of capital in the production process, then the capital stock does grow, symbolized here by this additional treasure. Now, if we go from the first production period to the second production period, we have now a larger capital stock due to this additional treasure. So firms can produce a somewhat larger cake. This is what we call economic growth. And then households make again their consumption savings decision, decide how much of this cake is consumed, how much of this cake is used for saving purposes. The capital market takes care that savings supply by households equals investment demand by private companies. If investment demand by private companies is larger as the depreciation of physical capital, the capital stock grows once again, and we can add an additional treasure to the capital stock. Now, in transition to production period 3, the capital stock is once again larger. So the cake gets once again a little bit larger, GDP gets larger. Households decide once again how much of this larger GDP cake is now used for consumption purposes, how much is offered on the capital market as savings supply. The capital market interest rate adjusts in a way that savings equal investment, and then if investment demand by firms is larger than depreciation of capital, the capital stock growth once again, and as a result we can add an additional treasure to our capital stock here in this example. And so on. This is the way how the Solow-Swan model explains why the GDP cake gets larger and larger. It gets larger and larger because we add more and more physical capital to the production process. If you compare now the initial size of the GDP cake with the final size we have reached in period 3, the difference of these sizes is real GDP growth. That is a quite simple way to demonstrate the mechanics of the Solow-Swan model based on our circular flow model. As a result, the question how long does GDP growth goes on is identical with the question how long does the capital stock grow. The answer is as long as gross investment, symbolized by capital letter I of a specific year t, is larger than capital depreciation in this year, here symbolized by the depreciation ratio lambda times the size of the capital stock. We can therefore write down the following accumulation equation. The capital stock of the next year t plus 1 is equal to the capital stock of this year plus gross investment of this year minus capital depreciation, represented by the product of the depreciation ratio lambda times the capital stock of this year. If gross investment is larger than depreciation, this number is larger than this number, then the capital stock of the next year will be larger than the capital stock of this year. So in this case, we would have capital stock growth. If gross investment is just equal to capital depreciation, then this growth stops and the capital stock of this year is equal to the capital stock of the next year. So we need gross investment larger than capital depreciation to have economic growth, in other words. If we have reached a state of the economy where total savings results in total gross investment, which is equal to depreciation, capital stock growth terminates, and we cannot add an additional treasure to our capital stock in this symbolized version of the circular flow model, and therefore we have not a larger capital stock in the next period, and as a result GDP growth, the size of this cake, stays constant. So we have reached the end of the accumulation process. The economy is in a steady state. It does not grow, but it does also not shrink. GDP simply stays constant from one year to the next year. Consequently, the Solow-Swan model has the implication that for a given amount of production factors, an economy finally reaches a state where it neither grows nor shrinks. This state is called the steady state. When this state is reached, depends on one hand on the level of savings and, as we've seen, on the other hand, on the level of capital depreciation. The higher yearly savings and the lower yearly depreciation, the higher is the steady state level of the capital stock and hence the steady state level of GDP. Okay, this was the demonstration of the basic idea of the Solow-Swan model with the help of the circular flow model. Next, I would like to develop a graphical exposition of the Solow-Swan model, which is a little bit more accurate. To simplify the graphical exposition, we assume that savings are always a constant fraction of household income. So we make this assumption. Savings of household is equal a constant percentage fraction of household income. We use the shortcuts as we have done so far. Total savings is capital letter S, the savings ratio is small letter s, and income or GDP is symbolized by I. To make a numerical example, if the savings ratio is 10%, S would be 0.1. If income would be equal to 100,000 euro, then savings ratio times income yields a value of 10,000 euro. From an empirical point of view, savings ratio of most countries lie in the range of 5% to 15% of disposable income of households. Germany has a quite constant savings ratio of roughly spoken 11% of disposable income of German households. 11% of disposable income is saved every year. Okay, this is one simplifying assumption. So the potential effect of the interest rate on savings is neglected. This is only a simplification. The Solow-Swan model is presented now in a GDP physical capital diagram. This means we measure GDP on the ordinate, also sometimes called y-axis. The shortcut of GDP is also y, and the stock of physical capital is measured on the abscissa or x-axis. The shortcut of physical capital is, as we know, capital letter K. The production function of GDP, this economy, is symbolized by this red curve. GDP is a function of input factors. It's written in this way. this is GDP dependent on these input factors. So let me explain what kind of input factors are symbolized by these shortcuts. A measures the input of technological knowledge. So this is, for example, the number of blueprints available in an economy. B measures the input of land and natural resources. P measures the input of public goods like infrastructure, communication infrastructure, traffic infrastructure, or also the legal system of an economy. L measures the input of physical labor. This means the mere physical working power of workers. Capital letter H measures the input of human capital. This means the qualification of the workers. And finally, capital letter K measures, as we know, physical capital. For example, the value of machines, production buildings, or transport fleets of companies of the economy. All production factors, with exception of the capital stock, are held constant in this diagram. So A, B, P, L and H are constant, only the capital stock is varied along the abscissa. In this point the capital stock would be 0, and starting with this point and moving to the right, we increase the capital stock step by step, and as a result GDP grows step by step as symbolized by this red curve. Since we keep all other production factors in this diagram constant, physical capital displays decreasing marginal productivity, which means the GDP production curve dependent on physical capital gets flatter and flatter the more capital we use. For example, if we add the first machine to the production process, symbolized here by the length of one little quadrant, then GDP grows quite strongly by 1, 2, 3, 4 little quadrants. So this is the productivity of the first machine. If we now add a second machine, again symbolized by the length of one little quad, then GDP grows, but only in this case by additional 2 little quads, and so on. So if we add an additional machine on this capital stock level here, then GDP is growing only quite marginally with little additional amount compared to the strong increase for the first or second machine which we add to the production process. So this is what we call marginal productivity of machines. The explanation for this, the microeconomic explanation for this is, if you add more and more machines and keep, for example, the number of workers constant, as we have assumed here, then you have less and less workers per machine which are able to manage the machine. So the productivity of machines gets smaller if we add more and more machines and keep the number of workers constant. I think this is a quite intuitive and plausible idea. So that is the explanation why this red curve, which represents the GDP production function, gets flatter and flatter the more capital we add into the production process. If this curve now represents GDP dependent on the capital stock, how will the savings curve dependent on the capital stock look like? Since we have no foreign countries and no government, GDP is equal with household income. The Solo-Swan model assumes, as we have just seen, that the savings ratio is a constant number larger than 0 but smaller than 100%. As a result of this assumption, the savings curve lies above the abscissa but below the GDP curve. It is smaller than 100% of GDP but larger than 0, so the savings curve must lie somewhere in between in this area, as for example symbolized by this green curve. The savings function is a certain percentage according to the savings ratio times GDP. So the GDP production function appears here also, is only multiplied with the savings ratio, which is larger than 0 but smaller than 100%. Okay, now we have determined the savings level in this economy depending on the capital stock. Next question is now, what do households make with their savings? Well, I guess we know it already. They offer their savings as credits to the capital market. Who demands household savings on the capital market? Who's on the demand side of this market? Well, the company sector, the firms of the economy. What equilibrates now household savings with firms' demand for credits? That is something we still have to discuss. It is the capital market interest rate. Capital market interest rate adjusts in a way that by the end of the adjustment process, household savings equal credit demand by firms. The following diagram shows how the capital market does all this in the background of the model. In this capital market diagram, we measure the interest rate on the ordinate axis here and the savings supply and investment credit demand on the abscissa axis. Savings depend under the simplifying assumptions of the Solo-Swan model not on the interest rate, as we have seen, but is equal to the GDP level times the savings ratio. In this diagram, therefore, savings supply is such a vertical line, not depending on the interest rate, but only on GDP level times the savings ratio. The investment credit demand curve depends, as usual, in a negative way on the interest rate. Consequently, it has a negative slope, like this. So, the lower the interest rate, the larger investment credit demand. The intersection point between savings supply and investment credit demand represents the market equilibrium interest rate. If caused by, let's say, a stochastic shock, a random shock, the interest rate gets higher, excess supply would result, savings would be larger than credit demand, and as always, in case of excess supply, the interest rate decreases, so it falls back towards the equilibrium level. If the opposite happens, for random reasons, if we would have a fall of the interest rate by chance to a level lower than the market equilibrium interest rate, we would experience excess demand, interest would be too low. And if there is excess demand, then the interest rate grows. Excess demand causes a growing interest rate, so we move again back towards the market equilibrium interest rate. In case of such a stochastic shock, all these adjustment processes take place immediately, such that the market equilibrium interest rate prevails always. As a result, we can assume that savings supply always equals investment demand. So the market mechanism of the capital market takes care for the equivalence of investment and savings. As a result, in the following analysis, we can simply assume that savings is always equal to investment. Now we can take this knowledge and use it in our Solo-Swan diagram. We have already seen that here the green line represents savings supply. Now we have learned that the capital market makes sure that savings always equal investment demand. So the green curve is not only savings supply curve, but also the curve that measures total investment, gross investment in this economy. Okay, that's an important point. So green line is savings as well as investment curve. To complete the Solo-Swan model, we have to add now only the depreciation curve. The depreciation is always a certain percentage share of the capital stock. As a result, the depreciation curve is a straight line, like this bright blue line here. It is the capital stock measured on this axis times the constant depreciation ratio expressed or symbolized by lambda. This capital depreciation curve implies a quite high depreciation ratio. For a capital stock equal to the length of 7 little quadrants, 1, 2, 3, 4, 5, 6, 7, total depreciation equals the length of 5 little quads, 1, 2, 3, 4, 5. As a result, the depreciation ratio lambda equals exactly 5/7, which is 71% roughly. So this curve here implies a lambda equal to 71%. So this is certainly a very high depreciation ratio, not very realistic. In Germany we have an empirical depreciation ratio for the total capital stock of the economy of around 3%. We use this very high depreciation ratio here only because it makes the graphical exposition of the Solo-Swan model simpler. If you would use more realistic depreciation ratio like 3%, this bright blue curve here would be very, very flat around here, and as we will see in the following, this would make the total analysis graphically quite complicated. So this is the explanation for the very high depreciation ratio. Now that we have completed the Solo-Swan model, we can start the analysis to what level, for example, the economy grows if we start with a certain, let's say, historically given level of capital stock, like this capital stock level here. We will do this analysis in our next lesson. So much for now.